All right, so we have water cooled at from 500 degrees Celsius and 100 bar at a constant pressure to a final specific volume of 0.01 meters cubed per kilogram. We want to find the final temperature and the quality if it's two-phase, and then we'll draw things on a TV or a PV diagram. Okay, perfect. So I will need the temperature and pressure and specific volume at all three states, at both states. And then, of course, the quality if it's necessary. So at state 1, what I'm missing is the specific volume. So the first thing I'm going to do is I'm going to figure out what phase I'm in. Now, if I go to table A2, remember we are at we are T1, 500 degrees Celsius, and P1 is 100 bar. And if I go to table A2, the saturated tables that are organized by temperature, I'll notice that I sort of drop off the face of the Earth after 374.14. So this is the critical temperature. The critical temperature is specific for whatever substance that you're talking about, and it's the highest temperature at which liquid and vapor can coexist, right? And as a saturated substance. If we're above that critical temperature, then you can only have a single phase, okay? So let's look at the pressure. Let's go to those saturated tables. So here I could see we're at 100 degrees Celsius, and I could see that I am above that critical or above that saturation temperature. So by table A3, since my T2 is greater than Tsat, it is superheated. Okay. Now, if both the critical temperature and the critical pressure were exceeded, then it would be classified as what's called a supercritical fluid. All those properties are still available in your superheated tables. So a supercritical fluid, it's not really a vapor. It's not really a liquid. It has properties of both, but if you had to describe it, it probably looks more like a gas. Okay, it's invisible. Very high temperature, very high pressure, supercritical steam. For our purposes, what it really means when we look up property data is we go to our superheated tables. That's where all that data is going to be. So if you find yourself, if you're above that critical temperature, you're going to be going to your superheated tables, okay? So, all right, so I'm going to my superheated tables. 100 bar, 500. So that's going to be between those two. I could interpolate. I could go through that math, or I could see that I'm right between the two. So whether you interpolate or whether you take the average, you're going to get the exact same thing, which is, let's see. So my specific volume, V1, 0.03394 meters cubed per kilogram. Perfect. So I think I got everything for state 1. Now I need to go to state 2. So state 2, I got a P2 of 100 bar. I have a specific volume. Oops. There we go. V2 of 0.01 meters cubed per kilogram. Let's go to our saturated tables just to see what phase we're in. And look at that. At 100 bar, we are actually between our V sub F of 0.0014 and change and 0.018 and change. So I know it's saturated. So that tells me, well, so it's saturated. That tells me that at 100 bar, the only temperature that it could be is going to be my saturation temperature. There we go, which is 311.1 degrees Celsius. So that's one of the things I'm supposed to get. The other thing I'm supposed to get is my quality, right? Because it is saturated, so there is a quality associated with this substance. I know V2 is equal to V sub F plus my quality times my V sub G minus V sub F, or I could call that V sub FG. So my quality ends up being V2, 0.01, minus my V sub F, 0.0014524 over V sub G, 0.01803, minus V sub F, 0.0014524. So let's see, what do I get? Great question. I got 0.52. So 0.52. So I am going to box that right there. All right, perfect. Now, I went ahead and drew my temperature, my TV, and my PV diagram. So let's look at it. And before we look at those tables or those diagrams, let's think about. So state 1, it's going to be a superheated gas. But on my TV diagram, that temperature is going to be above the critical temperature of 374.14. So we'll see what that looks like. At P2, or at state 2, we're two-phase, so it's going to be underneath the dome. Okay, so let's go look. So here's my TV diagram. Let's make a note of a couple of things. So number 1, this temperature right here, that corresponds to that critical temperature. It was, again, 374.14 degrees Celsius, and we're at 500, so we're going to be above that, right? And here's our T2, or saturation temperature at 100 bar. It's a constant pressure process, so you notice that we've gone along a line of constant pressure. I've also noted what the specific volumes at state 1 and state 2 are. And yeah, there you go. Now let's go over here to our PV diagram. So this is in that superheated region. This is also in that superheated region. So on our PV diagram, this guy right here, this is actually what corresponds to our critical pressure. And that critical pressure is specific to whatever substance it is. That's going to be, let's see, I think 220.9. Perfect. So yeah, there you go. So that's going to be right here. So it looks like our pressure right here is about right in correlation with the top of that dome. So, all right. So hopefully that's helpful. Let me know if you have any questions.